Okay, as promised, we are moving on to continuous distributions, and we are starting with talking about the normal distribution. This is the probability distribution that we like to, um, that's the easiest to do things with, and we tend to assume that our first assumption tends to be that our data should fit this distribution. That's what most of the statistics are built around using. Um, so let's talk about what the properties of a normal distribution are. So it is a continuous probability distribution. So rather than being discrete values like 1, 2, 3, like what you get from rolling a die, or like what you get from flipping a coin, it's continuous. There's an infinite number of possibilities between 1 and 2 in a continuous distribution, etc. Um, it's completely defined by its mean and standard deviation. Graphically, if we were to draw a curve over a standard deviation, it's going to be a symmetric bell-shaped curve, shaped kind of like a bell. And if you could imagine a handle sticking out of the here at the top where the mean is, would look like a handbell kind of. It is centered right above the mean of the distribution. There's our mean. Then we've got values at 1, 2, 3, 4, etc. standard deviations on out. Symmetrical, so if you look at just 1/2, this side is identical to this side. The bell shape implies that most of the data is here in the middle. So we've got an example of here where it's symmetric and bell-shaped. This one is symmetric. If we drew an imaginary line right down the center here and folded it over, there wouldn't be any weird overlap. It'd be nicely symmetric. Another thing to note is that it approaches the x-axis here on both ends, but it doesn't ever actually touch it or cross it. So, like so, not like so. So, these are the properties. Total area under the normal distribution curve is 1. It is completely defined by the mean and the standard deviation. It is bell-shaped and symmetric. It approaches but never actually touches or crosses the x-axis. That's what an asymptote is. So, as you can imagine, there are an infinite number of possibilities for what this actually ends up looking like depending on the data. It can be fairly tall and thin, it can be fairly broad, it can be very broad. It moves with wherever the mean is. So to avoid having to do separate probability calculations for each normal distribution, I am going to add one thing here. Let me go back to this curve. It's kind of hard to see, but right here at one standard deviation away from the mean, and likewise on this side, the curve shifts from being a downward pointed curve to being an upward pointed curve. It inflects at that point, and that is how the standard deviation defines what the curve looks like. That's where it shifts from curving down to cover things and curving up, that happens at the 1 standard deviation. Okay, so to avoid having to do lots of repeat calculations, we standardize the curves, and we convert it to a standard normal deviation. So rather than having to compute the area under each different curve, what we do is we convert all the values to, in essence, distance from the mean in terms of standard deviation. It has the exact same properties, almost. It's still bell-shaped and symmetric. It's still completely defined by its mean, which becomes 0 in this case, and its standard deviation, which now becomes 1. The total area is equal to 1, and it still uses the x-axis as a horizontal asymptote. So to do this standardization, we convert each x value to a standard score. We did talk about standard scores a while ago. The example I gave mostly was with standardized test scores and percentiles. No, sorry, that was with percentiles. I don't think I had a good example for standardized scores. This is a good example for where standardized scores come in useful. In essence, we take the value of the probability. We take the value, we subtract off the mean, and we divide by the standard deviation, and that becomes our standard score, or z. So what that does is it converts our things. This could be 20 and 10 and 30 or whatever. We subtract the mean from the mean and get 0, so that turns that into a 0. We subtract if this is 1 standard deviation, we subtract the 1 standard deviation, we subtract the mean from this and divide by the standard deviation, we get 1. So we've converted that to 1 for our standard deviation. So we've just standardized the data. I've also heard it referred to as normalized sometimes. That's a slightly different context, though. We've converted it to a more standard shape that then we can look at tables and stuff, and it's all calculated for us in advance, and we don't have to do the extra work. We just have to do this little bit of calculating here. Basically, instead of needing to know what this is, we know how many standard deviations away from the mean this is, and we're good. So if we've got a normal distribution with a mean of 48 and a standard deviation of 5, and we've got an x value that's 45, and we want to convert it to a z to indicate where it is on the standard normal distribution, we subtract off the mean and divide by the standard deviation and end up with negative 0.6. So we could draw these distributions like so. Our mean is 48. Standard deviations are 43. That is going to, we can get the curve and stuff the right shape by trying to match that, as I was saying, where the curve inflects. Then the value we're interested in of 45 is right here in between those. You convert it to a standard normal distribution. It's basically just relabeling those. Instead of being 45, we are 0.6 standard deviations below the mean. Okay, All right, and that is the end. We will spend more time on standard deviation, or not, sorry, on normal distributions and using them. Um, we will undoubtedly spend quite a bit more time using normal distributions and specifically what we can do with them from here.